Okay, so like I said, it's a fairly light, second half of the week in terms of reading. Basically, it just comes all down to Graham-Schmidt, and you've seen Graham-Schmidt before in 223. It's this process of how do you take a basis and how do you make it orthogonal, but now, of course, we're working with a generalized inner product in potentially an abstract vector space. So we start off with corollary 423, and it says that, okay, listen, if you give me an orthogonal set, and we look at the span of that orthogonal set, and then you give me a vector which does not lie in that span, then when I compute its orthogonal component, I get something which is non-zero. Okay, so really the essence of this corollary right here is this part. Okay, that this is non-zero, because we already know that if you have a span of a subspace and you compute v minus its projection, you'll get something which is orthogonal. But you're not guaranteed that what you get is non-zero because, well, 0 is orthogonal to everything. So that would have been a perfectly valid solution. So I can try and draw this, but again, we're kind of like appealing to my ability to draw in 3 dimensions. Right, so maybe this is, let's call that U per the question, and let's say the origin is right here, and I have some sort of like, ooh, why are all my lines squiggly? And I have some sort of vector V like that, and let's say I kind of like draw its shadow. So this is its projection. And then I'm going to compute its orthogonal part, right? So this, that's V minus the projection onto U of V. And the blue vector here was V to begin with. So what it says is you're guaranteed that this red thing is not the 0 vector, right? Because it always could be the 0 vector, but you're guaranteed by the corollary that's not the 0 vector. So that's all this corollary is saying, and it's not too big a deal. So I don't want you to worry too much about it, but what it's doing is it's sanity checking that the Graham-Schmidt orthogonalization process is going to make sense. So proposition 424 then says, okay, well, what you're going to do, let's say you're given this basis. So start off, we're going to do this by induction. Choose F1 to be really whatever basis vector you want, but usually we take it to be the first basis vector. And now what you're going to do is inductively, suppose that you've already chosen K, or I guess I used L here, L orthogonal vectors. Then you're going to take one of the vectors that does not live in that space, like this blue vector here, compute its orthogonal portion. And if that's non-zero, then you can add it to your set, and you've now increased the size of your orthogonal set. And of course, last week we showed that if you had a orthogonal set of non-zero vectors, they are linearly independent. So if you're at a finite dimensional vector space, of course, this process eventually has to terminate, because every time you're adding a new vector to your orthogonal set and it's linearly independent, then its size is increasing, and eventually it's going to hit that ceiling, which is the dimension of your space, and it has to stop there, right? You can't have more linearly independent elements than the dimension of your vector space. So this algorithm is eventually going to terminate, and that's kind of what we get from that. Okay. Now, computationally, this can be a little bit messy, just because there's a ton of inner products going on, and that is a fairly intensive bit of labor. So again, this is the sort of thing that you definitely will want to appeal to a calculator for wherever possible. Sometimes Wolfram Alpha will be the right thing to do. Sometimes Octave will be the right thing to do. So the example I want to do for this is, let's revisit the 2x2 matrices, because I think it's been a while since we did anything with them. All right, it's the 2x2 matrices with this inner product. AB is the trace of A transpose B. Okay, so I gave you this inner product in the notes, and said, go ahead and check whether it is or not, is an inner product or not. As a note, and I think I put this in the note, this is often called the Hilbert-Schmidt. Inner product. Now, Hilbert-Schmidt is sometimes reserved for when you're talking about really infinite dimensional vector spaces and you're looking at linear transformations on infinite dimensional vector spaces. There's actually an inner product there that you can do, which is defined much the same way. But a lot of us use it for the finite sense as well. There's also a sense in which this is actually the Euclidean inner product. Okay, and you might have to actually, if you haven't worked this out before, try it with two 2x2 matrices, right? Take two elements of M2R, multiply them together and compute their trace. And what you'll see is you would get the exact same inner product back as if you had taken all the columns of the matrices and stacked them on top of each other. So in this case, if you had a 2x2 matrix and you stacked all the columns, you would get a 4x1 column vector. And then if you were to take just the usual dot product, the Euclidean inner product between those 4x1 column vectors, you would get the exact same thing as in this trace here. Okay, so there's a sense in which this is the Euclidean inner product, even though it's now for matrices. So that idea of thinking of the 2x2 matrices as Euclidean R4, that's going to be the notion of an isometry, which we'll talk about next week, okay? But try it out and see that it actually works out correctly. Now, in my case, this is fairly easy to code into Octave, to just write a little function which will output this for you. Of course, you can just do it by hand if you want, but it's pretty easy to do this in Octave, so I recommend playing with that and seeing if you can do it. Okay, now, you don't technically have to start with a basis, but I am going to start with one just to, so we have easy reference to what vectors we're going to plug in. One, zero, zero, one, just the identity matrix, and the off diagonal like this. Okay, so this is our matrix. You can check this is not orthogonal. Okay, basically, really, if you took any two of these and plugged it into that inner product, you're not going to get zero. And we're going to say use this to find an orthogonal basis. Okay. All right. Now, of course, this might seem a little bit weird that, I've given you a basis and then said find an orthogonal basis, but that's more or less how Gram-Schmidt works. Often you start with a basis and you use it to orthogonalize. You orthogonalize it with Gram-Schmidt, you get an orthogonal basis out. So the interesting thing here is that if you change the basis that you put in, or even change the order in which you perform the Gram-Schmidt orthogonalization, you could get different bases out. So I'm going to go through this example, and I'm going to hit these basis elements in order, left to right. And what I would recommend that you do is, as practice, change the order of the bases around, or maybe take one of the basis elements and make it 1, 1, 1, 1, or something like that, and see how that change propagates throughout the algorithm and gives you really an entirely different basis. So the Gram-Schmidt orthogonalization algorithm is highly dependent on what basis you provide it and the order in which you do it, okay? But let's go through and let's just do kind of a little example here. I'm going to, let me just label these matrices. I'm going to call them A, B, C, and D. Okay, just so that I can refer to them without having to write them down every time. And the first thing we're going to do, so I'm going to let a hat, I'm going to let the hat indicate my orthogonal basis vectors. Now, according to the algorithm, frankly, I can choose any one of the four of these to start with, but I am, of course, going to take just the matrix A. Okay, and that's it. That's how you start the algorithm. You just choose one of them and let that be the first thing. Now, for the next vector, so what we're going to do is we're going to take B and then subtract its projection onto the span of A. Right, like this. Now I've worked out what this is ahead of time. Okay, but you can double check me. So the inner product of B and A is just 1, and then the norm squared of A ends up being 2. So you can work all of this out, and if you do that, you're going to get 1/2, -1/2, 1, and 0. Okay, now the great thing is, so first of all, this has fractions in it, and almost any time you do the Gram-Schmidt orthogonality algorithm, you're going to get fractions, and that sucks. But the thing is, you can get rid of those fractions because we're not talking about orthonormal, we just want orthogonal. So if you start off, are you meaning to multiply 1/2 by a different matrix? Oh yeah, sorry, that should be A. Thank you. Perfect, thanks. Okay, so if you have two vectors, what you want to do is, because you're not worried about orthonormality, you can take one of these vectors and you can make it bigger, right? And you would still preserve orthogonality. And the linearity of the inner product tells you that. So if you take one of these vectors and you make it smaller or you make it bigger, they're still orthogonal. So this matrix has these nasty fractions inside of it, meaning that I can take any scalar multiple of it and preserve its orthogonality. So I'm going to probably multiply this matrix by 2. I think that's probably the best thing you could do. Of course, you can multiply it by anything that you want. Okay. Oh, sorry, that should be a 2. So I multiply this matrix by 2, and this is the thing that I get out. And of course, at this point, you can go back and you can double check that A and B hat are in fact orthogonal to each other, just to make sure that you haven't made any mistakes, right? Because if they're not orthogonal, you must have made a computational error. So you can just double check that pretty easily. Okay. And now for C, we're going to do the same thing. So C on A hat. Now, the other thing to note here is that once you've computed this denominator, notice that this denominator is not changing. I'll show you what I mean by that. Okay, so C was the identity matrix, 1, 0, 0, 1. And it turns out if you work it out, you get exactly the same fraction there. You get 1/2, 1, 1, 0, 0. And then if we compute the inner product of C and B, you do get 1, but now the norm of B is 6. 1, -1, 2, 0, like that. Okay, and yeah, the point that I'm making here is this computation also occurred up here, right? So the great thing is that once you've already done that, write it down somewhere so you have it, because you're going to keep using this fact over and over and over again, right? And so you don't have to go back and redo that computation. And same thing with the norm squared of B hat here. You imagine in the next computation, that thing is going to show up again. So just write it down somewhere so you know what it is. And in this case, it's 6. Right? So just something to keep in mind there to save yourself a little bit of work. And if you go through this, let's see, what do you get? You get this vector. Turns out quite nicely. And again, I can take any scalar multiple of this thing. So I'm going to multiply this thing by 3. C hat to be 1, -1, -1, 3, like that. Okay, and finally, we've got one last vector to do. Could we do this in Octave? Absolutely. So I actually programmed something in Octave to do this. I can try and show you what it is if I've got some time here. And in fact, it's actually possible just to write a whole algorithm for Gram-Schmidt, where you just say, I'm going to give you the 4 vectors, and and as long as you can program what the inner product is, you can tell it to do the whole orthogonalization for you. Post what though, Coco? Like specifically, what are you referring to? Sure, I can if you want. So, and the same thing, you'll see in a second in the exercises that there are things we can do there. Oh, sorry, this should be D. But sure, I can show it to you. And then D, C hat. So, like I said, if you're a computer scientist, what you might want to actually do is, how do we know that A is 2? So I actually worked it out ahead of time to show you. So it's not like I just magically computed that in my head without, because I don't want to do a ton of 2x2 matrix calculations. I went and did all of it ahead of time. But if you guys want, I'll actually pull up Octave right now on the computer, and I'll show you guys how you would code this inner product to make it really easy for you to check these things. Okay, and so if we do this, we're going to get 0, 1, 1, 0. And then I think, yeah, this just ended up somehow, again, magically working out to a half. And then magically, again, 1/6 times b. Where was b? 1, negative 1, 2, 0. 1, negative 1, 2, 0. And then we got, okay, finally, the numbers get a little bit interesting when we get to c here. And you work this out, and it works out to be surprisingly nice. It is, let's see, so it's negative 1/2, 1/2, 1/2, 1/2. And so set d hat to be negative 1, 1, 1, 1, like that, okay? Thus, so our basis then is 1, 1, 0, 0, still preserved from the original one, and then all of our new vectors. And of course, we've lost some zeros. You know, it's not perhaps as nice as the last one, but like so, right? That's our basis like that. Okay. So yeah, if you guys want to see, I can try and do this for you. Let me see if I can. Okay, I'm going to share my screen here. Okay, I'm kind of doing this live, so give me, you know, try to be a little bit forgiving. Okay, so this is how you declare a function. I included this in the cheat sheet, right? You say function, whatever you're going to claim the return variable equals IP, that's the name of the function, and then your inputs A and B. So what I'm going to do is I'm going to say compute the trace of A transpose. Transpose in Octave is just the apostrophe there, times B. And then I'm going to suppress the output with a semicolon and then say end function. Okay, and I'll type this up if you guys want. So my matrix was originally that, and B was 1, 0, 1, 0, right? So I can compute like that, and that gives me 1. And Shail, you're asking how I knew that the inner product of A with itself was 2. There you go, there's your answer there, right? So if I actually wanted to do now Gram-Schmidt, I would do B minus the inner product of A and B divided by the inner product of A with itself times A. And that gives us that matrix. That is, hopefully, if you guys go back, if you've been taking notes, 1/2, -1/2, 1, 0, that is the matrix that I got out, right? So what I would do is I would set B hat to be 2 times that, right? And then if I were to do the next thing, I would do, okay, so I've got the matrix C. What was the definition of C? C was the identity matrix. I would do C minus the inner product of C with A divided by the inner product of A and A. Again, you don't have to do that. I know it's 2, right? But let's pretend we were doing it anyway. Inner product of C with B hat divided by the inner product of B hat with B hat times B hat rather. And voila. And again, hopefully you check your notes. That is the same thing I got out, 1/3, -1/3, -1/3, 1. And I'm going to set C hat to be 3 times that, right? So C hat equals 3 times the answer. And then D was finally this off diagonal thing. So I'm going to do D minus DA divided by IPA minus IP. The inner product of D with B hat. Don't forget to do D hat times B hat, IP, D with C hat divided by the inner product C hat times C hat. And right, that's the matrix that I got, right? -1/2, 1/2, 1/2, 1/2. and then I set d hat to be 2 times that. So does that, you guys see how I did that in Octave? And it was really convenient that I coded this thing called the inner product, right? So that like I could just plug it in wherever I want. And again, you can imagine if for those of you who do have some computer science experience, you could easily set this up as, with a for loop, you could just plug through and actually compute the Gram-Schmidt. The only thing you're going to run into trouble with is at each stage, I scaled the answer so that I didn't have nasty fractions. If you were to actually code this to do your entire Gram-Schmidt from start to finish, you're probably going to leave the fractions in there. So the answers that you get out might be a little bit on the messier side, right? And it might even be possible that Octave has a Gram-Schmidt orthogonalization built into it, but that's, we'd have to look into that. I actually don't know if that's true. Okay, so does that make sense? Are there any questions about the Octave part there? Did you guys see how that worked and what that did? Makes your life a little bit easier, right? Mm-hmm. Can you imagine having to do this by hand, right? Again, like if you had this, didn't have access to a computer, I mean, probably I'd give you something a little bit easier, right? But this is actually a fair amount of work, and in Octave, it ends up being pretty quick. Okay. Now, that being said, this is a very, like you can imagine, this inner product it played very nicely with Octave. But there are some inner products which Octave does not play nicely with. So for example, when you, remember when we were working with the degree 2 polynomials and we were integrating them from 0 to 1, Octave's not super good at that. It's not good at like symbolic calculation. It might be able to do it. I'd have to look into it a little bit more, but it's not super great at that. Though again, you could have still coded it if you're clever. And yeah, so you have to, this isn't necessarily always the way to go. Sometimes it's faster to plug things into Wolfram Alpha, like legitimately, okay? So what I wanna do very quickly then is let's take a look at the first, so there are exercises posted for this week. And if you go and you pull up those exercises, actually, I guess I can just share my screen again. Right? So we have, it's really just one question, but nah, it's like 3 questions, right? So we've got the degree 2 polynomials, and we've got our standard basis here, 1x, x squared. And I've given you 3 inner products, okay? And we've seen these 2 before. We've seen the second inner product, and we've seen the third inner product before, but maybe you haven't seen the first inner product yet, and that's okay. And so basically the idea is to use this basis to compute the, perform the Gram-Schmidt orthogonalization algorithm with respect to each of these inner products. Now, obviously, as I change the inner product, I will get different orthogonal bases simply because I've changed what it means to be orthogonal, right? So what I want you to do, I just want to give you a couple of minutes because we don't have too much time, and just see if you can do it with the first inner product. So I know that this inner product looks freaky. It's actually really simple, okay? Just let's spend 5 minutes and see if you guys can grind that out. Okay, so that obviously wasn't a lot of time, but did anyone make any progress? Did anyone figure out what if you apply this algorithm, what did you get? Did the first one just cancel out to 0? What is, I mean, it depends on what you mean by, I mean, yeah. So actually, what I think what you're trying to say, Coco, is like this basis is already orthogonal in the one inner product, right? So I hope you guys see that. So in the one inner product, this basis is already orthogonal, right? It's so I got 1x. Yeah, it's just itself, right? And so that's what happens. If you apply Gram-Schmidt to a basis which is already orthogonal, it just returns itself. And this might look like a weird inner product. It's really not, right? So let's say I give you two polynomials. Does anyone recognize this? Do you guys know what inner product this is? I think you do. You've worked with it a lot. Okay, so let's say here's a typical polynomial, right? A1 plus B1x plus Cx squared. So if I just compute P0, the 0th derivative, at 0, I get A1, right? If I differentiate it, I get B1 plus 2C1x. So if I compute that at 0, I just get B1. And then if I differentiate again, I'm going to get C1, just C1. And if I compute P2 of 0 divided by, 2C1 divided by 2, I just get C1. Okay, so each of those things, Pi0 divided by I factorial just plucks out the coefficients. And so what this means is that if you compute A1 plus B1x plus C1x squared, A2 plus B2x plus C2x squared, this is A1, A2 plus B1, B2 plus C1, C2. Right? Yeah, right? Yeah, so Aaron, I think you must have seen this. And that's just, if you think of this thing as just being A, B, C, or A1, B1, C1, and this thing as just being A2, B2, C2, then this is the Euclidean inner product, right? So even though this one looks a little bit weird, this inner product is the Euclidean inner product on the degree 2 polynomials. And then think about 1x squared, that's the standard basis in that thing, right? Which is orthogonal. So for number 1 there, that one is, I just wanted to show you like what does that inner product look like if you actually want to write it on the polynomials. It looks complicated, but it's really not. Now P2 and P3. So P2 I want you guys to try, and in particular I want you to try it in octave because it's actually a little bit tricky to do in octave, but it can definitely be done. And then the inner product 3 is the most work. Use something like Wolfram Alpha to check your answer there because you'll have to integrate. But you already know what the answer is because every time you guys saw me do a basis with this inner product, I used that basis, right? It was like 1 minus 2x, 1 plus 6x minus 6x squared. That's the answer. You'll get that because that's how I found that basis, right? As I applied Gram-Schmidt to the standard basis with this inner product. So you know what the answer is, and you can double check against that. Okay, so give that a shot. I'll post the solutions in a little bit, and you'll be able to double check your work against that as well. Okay, so for those of you as well who still need to fill out your course evaluations, please go do that. Like I said, they mean a lot to me. They really are important. Otherwise, have a good weekend. Study well for next week. Post stuff on Piazza, and I'll see you all next week. I will say pro as well. I'll take that as well.